So next talk will be done by Shahaf Bassan. Shahaf, you're a PhD student in computer science at the Hebrew University. Mainly your research is focused on formal methods and formal explainability, mainly targeting computer vision, but also natural language processing and robotics. Thank you, Shahaf, for this presentation, and the floor is yours.
So thanks, Melanie. So I'm Shahaf. I'm from the Hebrew University. And my supervisor, I hope everyone can hear me. My supervisor is Guy Katz, as Melanie also mentioned. And I will be talking about towards formally verifying and explaining deep neural networks. Okay, so machine learning and neural networks are everywhere, as you all know. They are deployed in safety critical systems such as healthcare, autonomous driving, and in large language models such as ChatGPT that we all love, and many other models as well. Neural networks are also notoriously known to be sensitive to small input perturbations and adversarial attack, and to exhibit many mistakes and errors. This is a very well-known example that I guess that all of you already saw. We have a classifier that predicted that this is an image of a panda. We add some random noise onto it, and then the classifier predicts it with high confidence as a gibbon, and this is a very famous example. Another famous example is this one, where we can change one specific pixel in an image, and this will cause the classification to change. This is called a one-pixel attack. And both of these examples are just given you to show you how sensitive in practice neural networks are. And this is, of course, very concerning because we are using these models in safety critical systems. So we are supposed to be concerned about this. Okay, so now I want to ask the general question. Melanie talked about it a bit. And can we formally prove that a neural network is correct? So I'll talk a bit of what I mean by formally prove and what do I mean by correct in this term. But we'll dig into this more. So in the neural network verification configuration, we generally have a verifier. We have some neural network and some property which we want to verify. And the verifier usually returns one of two results, either a SAT result, which means that this property was satisfied, or an unsat result, which means that this property was not satisfied. So let's see a very, very simple example for a property. So we have a simple small neural network here, and the property that we're verifying is if the output can be larger than 60. We're asking if the output in this neural network can be larger than 60. And in this particular scenario, the answer is SAT, meaning that we found some satisfiable example. We found an input, in this case 1 and 3, such that the output is larger than 60, 65 in this case. Now we're asking a different property, can the output be larger than 70? And in this particular case, the answer is unsat, meaning that there doesn't exist any possible input such that the output will be larger than 70. So DNN verification is a very computationally hard process. It was proven that this process is NP complete. And nevertheless, like Melanie mentioned, there are many different tools and frameworks that were suggested throughout the years for verifying neural networks efficiently. Some of them are incomplete or complete methods, but this field in general is improving rapidly. So just to give you a sense, in 2017, the biggest networks that were capable of being verified by the best verification tools had only less than 100 neurons. So there were really great research papers that were held on networks with 3 neurons or 5 neurons or 10 neurons. But today, modern tools can verify hundreds of thousands to millions of neurons. So this is still not applicable to state-of-the-art tools like the OpenAI models that use trillions of neurons, but we're getting there. So this field is improving rapidly, and hopefully in the years to come, we could verify also state-of-the-art models as well. But now I want to talk about another aspect. I want to talk about this part of this equation, and what are the properties that can we even verify? Why do we even care that we have this thing of neural network verification? What interesting properties can we verify? And Melanie also mentioned a few, but I'll dig into a few other properties right now. So the first very commonly referred property is the property of adversarial robustness. So I'll talk a bit more of how this works. So again, we have a neural network, we have the image of a panda, and this image is classified as a panda, but we want to check that it is adversarial robust under some area. So we can encode a property that asks if there is an adversarial perturbation around this specific image, and this epsilon of 0.008 is the epsilon ball around this image, meaning that we let each one of the pixels change by up to a difference of 0.008. And this is the property that we're encoding. We can simply encode this as a DNN verification property and ask the verifier whether there exists some adversarial perturbation under this area for this image. And if the result is set, then we find some specific image and some specific perturbation such that the classification can change to a different class, meaning that we formally proved that this neural network is not robust under this specific environment of epsilon. But now we can decrease this epsilon by a bit, and now we're asking if there exists an adversarial perturbation in a smaller area of 0.006 instead of 8. And in this particular case, the result is unset, meaning that we formally proved, in this case, with our verifier, that we are robust under this specific epsilon and this specific image. So this is how we can prove, for instance, the adversarial robustness in some local area for a given image and a model. So now I want to talk about other properties that we may be able to look at for DNN verification. And specifically, I'm going to ask whether neural network verification can be used in order to formally explain the decisions of neural networks. So I skipped this. The field of AI explainability, I know that we had a full session on this yesterday, and we talked about it thoroughly, but in general, I'll just do a short recap. This is the field that we're suggesting tools and frameworks for explaining the decisions of ML models. I'll go over this pretty quickly because I'm sure that many of you know it, and we already talked about this yesterday. But this is a very simple example. We have an image that is classified as a Labrador, and we want to explain this decision. This is a very complex function. You can think of it this way, a neural network that maps this image to this class, and we are asking why was this image classified to this class. So this instance was given to Lime, which is a very famous and popular explainability tool, I'm sure that many of you know, and some feature selection that was done on top of Lime. And these were the features that were pinpointed in this particular case as the important features responsible for the prediction of this instance. This is another famous example. In this particular case, the network was trained to classify between images of wolves and huskies. And in this particular case, this image was mistakenly classified as a wolf. This is clearly an image of a husky, but it was mistakenly classified as a wolf. And this was again given to Lime. And these were the features that were pinpointed. So the explainer pinpointed the features in the background of the ice. And what probably happened here was that this model was biased toward images of wolves in the background of ice. And when it saw this specific image, it mistakenly classified it as a husky. So these were just quick examples to show you again why AI explainability is important and why it can help us for better understanding our models so we can better trust them. But now I'm asking a different question because I already talked about trust. So now I'm asking the question is, can we trust the explainability models themselves? Can I trust, for example, Lime? And the problem is that explainability tools themselves are heuristic and they do not provide formal guarantees. Many of the common explainability tools used today. So if we can't trust the explainer, of course we can't trust the model, and we're back to the problem we started with. We introduced AI explainability so we can trust our models. And if we can't trust the explainer, then of course that this is a problem. And formal verification can be used in order to produce formal and provable explanations. So this is also a subfield that is developing by itself, and I will talk a little bit about this as well. So first we need to ask, how can we even define an explanation? How can we formally define an explanation? So of course this is a very a big open question, but I'll talk about a few different options on how we can define an explanation. So we consider again this example. We have an image of a beagle that was classified by our neural network as a beagle. And again, we're asking why was this image classified as a beagle, and we want to formally define why was this image classified as a beagle. So one particular way to go is with this notation. It's called an abductive explanation. So this is a bit confusing. Abductive explanation is usually the term within the formal verification community. Within the ML community is usually referred to as sufficiency or a sufficient reason. We talked a little bit about this yesterday as well. But what this means, it's a subset of features such that if we fix these features to their values and we let the complementary features take in on any possible value, then the classification remains the same. This is what an abductive explanation means. I'll show an example now. So up there in the left, we have an abductive explanation. It's a subset of features. If we fix these features to their values, then no matter what we put in the complementary features, the classification stays beagle. So if this holds, then we say that this subset of features up there is an abductive explanation. So this is one possible formal notation for an explanation that is common. So as you might have guessed, we can encode whether this subset of features is an abductive explanation using DNN verification. We can encode it as a neural network verification property. So what we do actually is we fix these features to their values. We let the complementary feature take in on any possible value, and we ask the DNN verifier whether the classification has to stay the same. So this can be done with a pretty trivial encoding for a DNN verifier. Of course, there can exist many different abductive explanations, and we want to find small abductive explanations. The smaller the set, the more meaningful the explanation is, because it contains less features. And specifically, I'll talk on how we can find locally minimal or preferably even globally minimal explanations. Of course, the smaller the explanation, the better. So we would want to find globally minimal explanations. So let's start with showing how DNN verification can be used for finding locally minimal abductive explanations. So again, we have some input. It was classified to class 1 and by this neural network. And again, we're asking why, and we want to produce some abductive explanation, some locally minimal abductive explanation. So we start by freeing this feature, meaning that we let this feature take in on any possible value, and we encode this configuration to the DNN verifier. We ask whether this configuration is an abductive explanation. So if this process was successful, we can continue on to the next feature, and now we're encoding a query where we're freeing both of these features. Both of these features can take in on any possible value. And let's say that this was again successful. We continue to the third feature. But now when we encode the query now, we find some counterexample, or in other words, we got a SAT result in our verifier. So what we do is we leave this pixel inside, and this feature inside, and we move on to the next one, and to the next one. And using a linear amount of queries, eventually we will converge to some locally minimal abductive explanation. So this is how we can find locally minimal abductive explanations using DNN verification. Now I'm asking a harder question. Can we find the globally minimal abductive explanation? And this, of course, requires an exponential number of queries in the worst case, which means that it is very hard. And I want to remind you that each query itself is NP-complete, meaning that this problem is very, very computationally hard. More specifically, it's P sigma 2 hard. I won't get into the theory too much, but it's very hard to compute this. And so now I'm going to show how this can still be approximated using verification tools. So now I'll explain, but before I get into that, I want to define something else. A contrastive explanation is the exact same opposite than an abductive explanation. This is another form of an explanation. It's a subset of features such that if we change these features, the classification can change. So usually the features themselves are referred to as contrastive explanations, and the values that they take are referred to as counterfactuals. And this can also be validated using DNN verification. So we again can come to a DNN verifier and code this property, and this can be done in a very similar way to abductive explanations. As you might have suspected, there is a relationship between abductive and contrastive explanation. There is a dual relationship between the two, and it was proven that the minimal heating set of all contrastive explanations is the globally minimal abductive explanations, and reversely, the minimal heating set itself can also be computed using verification tools, MaxSat or MILP solvers. I don't want to get into this too much, but I just want you to understand that now we have two ways in which we can compute these explanations. We can either use verification, or we can compute contrastive explanations, maybe also using verification, and then using another solver, which computes the minimal heating set, and again we arrive at an abductive explanation. So we can take advantage of this duality property so it can serve us. This is what we need to understand here, and I will be referring to a paper that we published pretty recently on in TACAS on how we can do this. So the framework which does this actually is composed of two threads that are working in parallel. We have the upper bounding thread, which starts with the entire input space and frees features one by one until converging to some minimal explanation, like I showed you before. The other thread does the exact same opposite. So it computes small contrastive explanations and computes a lower bound. And both of these threads, as you can see, are running in parallel, and they're trying to get as close as possible to the optimal explanation. They're trying to get to the middle by getting close to each other. Of course, the upper bounding thread computes some upper bound. The lower bounding thread computes some lower bound. So we can use this in order to compute an approximation. So now what we can do, we can find an explanation. We prove that this explanation is correct. And then we can also prove how close is it to the optimal explanation. So how minimal are we? And what happens in practice is because neural networks are very sensitive to small input perturbations, then small contrastive explanations exist. And this quality is important. We can take advantage of this fact. We can take advantage of the fact that neural networks are sensitive to small input perturbations, and we can find very small contrastive explanations. And then, using this, we can compute good lower bounds and find good approximations, although this problem is very computationally hard. So you can see this in this graph. We have the upper bound, the lower bound, and what you can see is, although we don't really get to the optimal explanation, we can get pretty close. And this happens due to the fact that neural networks are very, very sensitive to small input perturbations, so we can use this trick in order to compute good approximations. I'll talk briefly on how we can improve the efficiency of this process even more, and I'll go over this pretty briefly because some of it is quite technical, but you can see these as examples for how we can use different verification techniques in order to improve efficiency in general of verification. So we'll talk about a few techniques within the context of this work. And one technique is to take advantage of the relationship, the information flow between the two threads. Let's say that these two boxes are examples for contrastive explanations found by the lower thread. So we can we can traverse the search space and we don't need to verify them. So this can improve efficiency. We can search for counterexamples in the area of counterexamples that we found. So if we found some counterexamples, we can search for other counterexamples in the nearby area because counterexamples tend to be close to each other. They tend to be batched together. So we can take advantage of this fact as well in order to improve efficiency. Finally, we can use heuristic XAI techniques in order to perform our queries more efficiently. So in this particular case, assume that we use LIME or SHAP or some heuristic XAI technique to rate the features by their importance. So 1 is the most important feature, 9 is the least important feature, and now we can perform these queries in an ordering that makes more sense. We're looking at these heuristic XAI techniques, and we're using them to perform this process more efficiently. In this particular case, what we're doing is we're doing some binary search over this ordering, and we show that this can help us compute the explanations much more faster. So this is enough for his efficiency. I think that Mark will talk more about this in a more general, broader sense. But another concern with abductive explanations is that they tend to be too complex. So let's see this example. This is an example of an abductive explanation. So we successfully proved that this is for the MNIST dataset, of course. We successfully proved that this is a correct explanation. But as you can see, it's not too meaningful. We can't really understand what's happening here. The pixels in white are not part of the explanation, and the rest of the pixels are part of the explanation. So if this wasn't clear. And so, of course, we want to prove, to some way prove that our explanations are correct, but we also want to provide explanations that are meaningful. So they will be meaningful to humans. So this is what we're trying to do here. So we also talked about abductive bundle explanations. So a bundle is just simply a subset of features. So you can think of this as a partition of the entire input space. So now instead of providing explanations in terms of features, we can provide explanations in terms of bundles. In the field of computer vision, this is referred to as superpixels, if you know this. And this was already something that was thoroughly examined within heuristic XAI techniques. So many heuristic XAI techniques work with simplified inputs, but we also adjusted this to work for the formal case and to adjust the DNN verification properties so that they will work with simplified features. Of course, the union of all features in a bundle explanation is clearly an explanation itself, and hence the soundness remains, and we can also trust the abductive bundle explanation. It's also a provably correct explanation. And these are some examples. So first of all, the bundle configuration ran much more quickly, as you might have suspect, because our search space is much smaller. And the second thing is that the explanations tend to be less complex, as you can see here, which means that they are more meaningful. So to conclude, I talked generally about DNN verification, or the next talk will also dig into this more. And this field is advancing rapidly, so hopefully we can reach a phase where we can verify state-of-the-art models soon. Properties that we can verify include adversarial robustness and also formal explainability. Formal explainability is computationally challenged, but I showed you different techniques how we can still compute it. So just a short recap. So we don't actually find, we prove that the explanation is correct, and we don't really find the globally optimal explanation, but we can prove an approximation. So we can find something that's pretty close to the best possible explanation and prove that it is very close as well. So for future work, I'll talk about future work in DNN verification and in formal explainability. So in DNN verification, our lab in general is working on improving the scalability of this approach. So in many different techniques, such as abstraction techniques and more. We are also looking at other properties. So I mentioned adversarial robustness, formal explainability. Melanie also mentioned a few other properties, but there are many other properties that could be verified as well, such as simplification, verifying reinforcement learning, fairness. There are lots of works done in this area as well. For future work in formal explainability, we are looking at alternative definitions of explanations. So of course, as you might have known, there isn't one correct way to define an explanation. There are many different forms, and we are looking at other possible. I just talked about some of these forms. We're thinking about and working on formally verifying other forms of explanations. We're looking at improving the scalability of this entire approach. We're looking at other DNN architectures and formally explaining tasks other than just classification. So this is for the years to come, and thank you.
I see how formal verification can help us find a counterexample that could show that a network can be easily perturbed. What I don't see as clearly is how I can be convinced that because formal verification, this network is for sure not going to be perturbed. How would you convince me of this?
How is it robust, you mean? How can you verify? So this is actually what happens in the verify. So this is the difference between the SAT or the unsat result. The SAT corresponds to a specific instance that you found, and the unsat result corresponds to the fact that you didn't find any possible example. And for that reason, it would be robust. So lots of times when we encode the properties, we actually encode the negation of the property. If you want to encode the robustness, then you encode, you ask whether there does exist some perturbation, and if you get an unset result, then you prove that it is robust. I didn't want to get into that too much because it's a bit confusing to think about this that way, but that's what usually is done.
Okay, so you've kind of proven that it could not be, it is robust.
There doesn't exist any adversarial perturbation in that area. So that proves that it is robust.
Because in those methods, you still use some kind of heuristic. Like when you try to change some pixels, you know, the fact that you change one pixel depends.
within the verifier. So the verifier maybe works with some techniques in order to perform this more efficiently. But it still proves that there doesn't exist any possible perturbation.
Okay, thank you.
Thanks for the great talk. Maybe I can, with regards to the previous question, convince you a bit more. I will talk a bit about formal verification methods themselves. I have also a question. Have you looked at differences in explainability depending on the training methods? So have you observed that methods trained with adversarial or certifiable training are sufficiently easier to explain, especially with their bundle explanations?
You're meaning different...
Have smaller explanation sets.
It's an interesting direction, but we didn't look at that too much. But yes, maybe different training procedures or even different domains, like not necessarily computer vision. We do have a few works on different domains as well, but every different domain, of course, acts differently, and of course, different training procedures. But this is something interesting to look on more thoroughly.
Thanks.
So my turn. Thank you, Shahaf, for the great talk. It was really interesting. I got some questions about your methods. So first, I was wondering the bundles. It's an hyperparameter, and I guess that you can pick the size of the bundles. So have you noticed some instability of your methods given these parameters?
Yeah, so generally what we do is we do some this is what most heuristic XAI methods do as well. We do some segmentation process first. So we use some segmentation algorithm which finds the areas, and then we perform the verification on that. And what we also showed that we can find the approximation, we can compute these approximations, and then we can figure out how much did the segmentation affect the process, because we can prove how close the bundle explanation is to the globally minimal explanation, and that will provide some answer on how the segmentation itself affects the process.
One other question.
Yeah.
I was wondering first about the scalability of your method, especially given the input size. And I will just ask the second at the same time. It's more a proposal. We have seen yesterday that there are many XAI heuristics techniques that have really also good advantages, running faster and good visual meaning. But we also have this formal XAI track, and both community are not that much communicating.
Right.
Something that I would really be interested in is having some kind of formal XAI benchmark, like the kind of optimal sciencey map you could get, and see which heuristics are close to this formal.
Right. So it can also, like I spoke a really bit about how we can integrate the heuristic XAI models with the formal ones, but this is very interesting to look at, and we're also really interested in this direction on how we can combine between these two fields. This, of course, very important.
Okay, I'm going to go. Great talk, thanks. So I was wondering about, so in most perception tasks, right, we have like the feature learning part, and then we have the classification part. And I'm wondering, in your intuition, do adversarial attacks attack the feature learning part or the classification part? And maybe my intuition would be that it's probably not the feature learning part. And if that is the case, would it make any sense to do these kind of verification approaches like over the latent space rather than over the input directly, rather than segmenting the input, like actually doing it over the lower dimensional latent space?
Wow, that's a really good question. So there's lots of different works on how you can perform the verification over different parts, and maybe we're also looking at this within the context of explainability as well, of maybe looking at what I mentioned of the alternative definitions, maybe not looking at the entire input space, but just on a limited part. But this is a complex question of how do you define what is important and not important in that context, but this is a really good direction of looking at the latent space and maybe something of that direction. Yeah, so really good directions. Thanks.
All right. thank you for the talk. You mentioned somehow that you were leveraging the brittleness so that it's actually faster to get formal proof. Is it to say that it's harder to get this formal verification for robust models?
Yes, so that's a good question. This is something that we need to look at. I think that in other domains that are not, for example, vision, the problem is sometimes even more, the models are even sometimes less robust. Like in a NLP, for example, if you change one specific word, then that can change the entire meaning of the sentence. So this is even, the situation there can even be even harsher than in a computer vision. But yeah, that's interesting to look at on different models. But I think that the idea is that although this is really, really a complex problem computationally wise, because of the fact that even if you get some robust model, then okay, you will change 1 pixel, it won't cause the classification to change, but you can change 5 pixels, and it will probably cause the classification to change. And this happens because neural networks are very, very sensitive. And this is their advantage because this enables their expressivity as well. But I think that you'll still get good approximations. Maybe not that as good approximations, but still good approximations, although the problem is very computationally hard.
Okay, thank you.
Thank you very much for the talk. I would like to ask a question more on the verification part than formally.AI. For the moment, you showed only examples of local explanation for one single image. Do you work on more global verification?
Yeah.
For let's say, the set of inputs and not just locally around one.
Right, right. So we are looking at this as well. This is also work that we're having now on adjusting this to the global configuration. And we can also look maybe on environments as well. I think that they talked about this previously yesterday. So we can talk about maybe the entire input space, but also a good direction is looking at regions, like epsilon region that we can verify. But yes, verification lets us maybe look at different regions rather than just the specific input. So this is something, not specifically in this work, but we're looking on doing this as well.
Hello, thanks for the talk here. So the previous questions, I'm not quite clear with the response for the future and the classification level. Given that satisfiability problem, correct me if I'm wrong here, mostly reduces problem to 3 sat problems. And given the dimensionality of most machine learning problems with billions of parameters and things like that, how do you efficiently use satisfiability at your level to make any meaningful conclusion?
Yeah, so of course this is a hard question. And the next talk will also talk about other, more in depth into the verification process itself, and we'll explain how we can make it more scalable. We can also use some abstraction techniques, like I mentioned with the bundles, maybe looking at certain areas. And this is within the context of explainability at least. Sometimes it's not that meaningful to look at independent features. This is why most explainability techniques looked at simplified inputs, because it's not really meaningful to humans. Humans don't even think in these terms. Maybe computers or the models think in these terms, but the humans usually think of like areas of the picture when they imagine the explanation. So this is one possible way, and also improving the efficiency of the models. So some of these queries can run, although it's NP complete, some of these queries can run in like milliseconds. So you can perform many, many queries, and like the linear amount of queries, although it's a million inputs, if it's a million milliseconds, then it's not that bad. Maybe it's worth waiting that.
Thank you for your talk. I haven't totally understood how you freeze the subregions, because you said that you prove that there are no adversarial attacks, but how you do that? Do you test all the possibilities?
Yeah, so yes, so we are testing all possibilities, and as I answered before, we're also looking at relaxing these definitions, so not looking on everything, but looking on only a subset of the possibilities, proving it for subsets of possibilities. But yes, this is more technical regarding to the DNN verifier. So you have some input constraints and some output constraints when you encode the verification property. So you just fix all of the inputs to their values, and for this particular input, you let it be in some region. So this is what you can do for robustness and also for instance, for explainability. So this means that we free this feature. We let it take in on any possible value in some region.
Hi, thanks for the very interesting talk. I was wondering something. I heard that some formal verification methods are differentiable, and that people use that to improve robustness of networks. I was wondering if such strategy could be applied to this explainability methods, since you said that abductive explanations are sometimes too complex. Is it possible to use the differentiability to improve this point on the networks rather on the methods?
Yeah, of course. There are also, that's a good question. There are also many works on how we can use the results of the verification in order to improve other things. So for example, you can find adversarial examples and then use them for adversarial training and train a more robust network. And the same with explainability. Or maybe you can have some conclusions regarding the correctness or how the network works, and then you can use this for additional ways, and you can maybe do this iteratively. So add some adversarial examples, train the model again, and then find more adversarial examples, and do this iteratively until you get to a more robust network. Okay, so thank you.